My name is Daichi Yamagata. I'm an assistant professor at Osaka University, Japan. I'd like to talk about fast and exact outlier detection in metric spaces. First, let me define the problem in this study. We use large P to denote a set of n objects. Given a distance threshold R, neighbors of an object P are the other objects with no larger distance than the threshold. We assume that the distance satisfies metric. Distance-based outliers are the objects with less than k neighbors. The right figure shows an example where k is 5 and the space is the Euclidean space. Let's focus on the blue point. Because it has more than 5 neighbors, it is not an outlier. On the other hand, the red point has only one neighbor, so it is an outlier. The objective of this study is to detect all outliers exactly, quickly, and with a linear space to the data size. From now, I call this problem the OD. This study is motivated by applications and existing techniques of DoD. Direct applications of DoD are noise removal and abnormal phenomenon detection. Especially due to the widespread of machine learning, they become more important because machine learning applications usually deal with data with big size and variety type. So DoD techniques should scale to the data size, deal with metric spaces, and be robust to dimensionality. One straightforward solution is a nested loop. Clearly, it incurs a quadratic time to the size, and it is not feasible to big data. Tree-based filtering is also a classic technique, but it is efficient only for low-dimensional data, so this is not a good solution for high-dimensional data. There are some DoD algorithms which can be used in metric spaces, but they still have the same drawbacks. We have 3 main contributions. First, we proposed a new DoD algorithm. It is nearly output sensitive and does not suffer from the quadratic time. Besides, it is robust to dimensionality and easy to parallelize. Second, we proposed a new proximity graph to optimize our DoD algorithm. Last, we evaluated state-of-the-art and our algorithms on some real datasets with some distance functions. The results show that our algorithm is quite faster than the state-of-the-art. Our idea that solves the DoD problem is to solve the range counting problem quickly. Recall that the neighbors of an object is the other objects with no larger distance than the threshold. To identify whether the blue point is an outlier or not, we just need to know whether there are k objects in this space or not. Besides, the number of outliers is usually small, so it is important to quickly filter inliers, which means non-outliers. To achieve this, we want to access only neighbors for each object. To achieve this, we need a data structure that can prune objects far from a given object. Then we employ a proximity graph that is built offline. The left figure shows an example of a proximity graph. Each point is connected to points with small distances. Proximity graphs have some nice advantages. It is available in any metric spaces, and it is robust to dimensionality. This slide introduces an overview of our DoD algorithm. It is based on filter and verification framework and can employ any proximity graph. In the filtering phase, we run best first search, BFS, from an object, P, if it accesses K objects that satisfy the distance threshold. It is an inlier, so we can stop the BFS. We do this for each object. From the left figure, we can see that this algorithm efficiently filters inliers. After that, we verify non-filtered objects via linear scan. Actually, in both phases, each object is evaluated independently. So our algorithm is very easy to parallelize. Though I skipped the detail, the time complexity of our algorithm is related to the data size and the number of false positives in the filtering phase, and the number of outliers. Our algorithm has no false negatives, so it is accurate. However, in the filtering phase, inliers may have less count than K. So it incurs false positives, as shown in the left figure. For instance, this inlier can be a false positive. Now we have one challenge here. Eliminating false positives needs a very huge offline or space cost. So we developed a new proximity graph that can reduce the number of false positives in as much as possible manner with a reasonable time and space. This slide shows the steps for building our proximity graph, metric randomized proximity graph, MRPG. An important concept is monotonic path. This is a sequence of nodes beginning at an object P, and it is ordered by distance from P. If P has monotonic paths to its neighbors, it is easy to understand that we can reduce the number of false positives. If a graph has at least a monotonic path between arbitrary two nodes, it is an MSG, monotonic search graph. Efficiently building an MSG is actually hard. So we approximate it, which means MRPG is an approximation of MSG. In the first step, we build an approximate k-nearest neighbor graph. In this graph, each object has links to its approximate k-nearest neighbors. So we can expect that each object has high reachability to its neighbors. Essentially, this graph is built by NN descent, a state-of-the-art algorithm for building an approximate k-nearest neighbor graph. From a random graph, this algorithm iteratively updates approximate k-nearest neighbors of each object by computing distances to the objects existing within two hops. This is done until updates are converged. We extended this algorithm to further improve the efficiency. Random links actually delays the convergence, so we used BP-tree-based data partitioning to have accurate initial links. Plus, we skip any objects with no update of their approximate k-nearest neighbors. Last, we compute the exact k-nearest neighbors for objects with large distances to their approximate k-nearest neighbors. This is quite effective to detect outliers efficiently because such objects tend to be outliers. Please check our paper for detail. Next, we make the approximate k-nearest neighbor graph a strongly connected one to further improve reachability. An approximate k-nearest neighbor graph may have disjoint subgraphs, like the left figure. So we fix it. From now, we use pivots. They are randomly chosen objects in NN descent class. Pivots are shown by red points in the figures. Actually, this step is simple, and an overview is shown in the left figure. We learn BFS from a pivot, and if we find that some objects are not connected, we do approximate nearest neighbor search, where the query is a not yet accessed pivot. For instance, in this graph, the query is here. We make a link between the query and the result of this search to connect the subgraphs. In this figure, this link is generated. This is repeated until we access all objects. In the third step, we make monotonic passes. Given a random object P, we run 3-hop BFS from P. Then we run 2-hop BFS from random pivots that are close to P. We then create necessary links if we have no monotonic passes from P to the objects accessed during the BFS. In the middle figure, we can see that this pivot has no monotonic path to the right pivot. So this link is generated. We repeat these operations for each randomly picked object. Last, we remove unnecessary links. Actually, we optimized our DoD algorithm for MRPG, and it always traverses pivots. Now, let's consider objects Pi and Pj, which are connected by a link. For instance, this is Pi and this is Pj, and they have a common pivot. Here, the link between Pi and Pj is not necessary because they are traversed via the common pivot. So we remove all such links. Now I claim that all the steps need only time linear to the data size or fixed degree, large K. This means that the building time is linear to the data size. Efficiently building an effective proximity graph for DoD is not trivial. However, you can see that each step is surprisingly simple. To summarize, our result has 3 nice properties. It is efficient, it is effective, and it is simple. Now let's move to our experimental results. We evaluated state-of-the-art DoD algorithms, our algorithms with state-of-the-art proximity graphs, and our algorithm with MRPG. We use 7 real data sets and 5 distance functions. This slide introduces the results of offline time and index size. The building time of MRPG is faster than the other proximity graphs, with one exception. As for this exception, please refer to our paper. The index size of MRPG is affordable to recent main memory systems. The bottom figures show the time to build each proximity graph with different data sizes. You can see that MRPG has linear scalability. Next, online time. The winner is our algorithm with MRPG. It is much faster than the best among the state object. The red box shows the result of state object. The blue one shows the result of our algorithm with proximity graph. From this comparison result, it is clear that our approach, filter and verification, with proximity graph is faster than the state object. These figures show the scalability to the data size and the robustness to outlier ratio. We do not show the results of the state object because they are slower. In all tests, MRPG is best. Finally, I conclude this presentation. We proposed a new solution for the DoD problem. It is a filter and verification framework on a proximity graph. To optimize it, we propose MRPG. We theoretically analyze the performances of our DoD algorithm and MRPG building algorithm. Also, we empirically show that they are currently state of the art. That's all. Thank you for listening.